In this problem, we have a mechanism in which the wheel consists of a 4 kg rim of 250 millimeter radius with hub and spokes of negligible mass. The wheel is mounted on the 3 kg yoke OA with mass center at point G and with a radius of gyration of 350 millimeters. And if the assembly is released from rest in the horizontal position and if the wheel rolls on the circular surface, we have to find the velocity of point A when it reaches point A dash. And for this, we had a work energy relation, that is initial kinetic energy plus initial potential energy plus work done is equal to final kinetic energy plus final potential energy. But here the initial kinetic energy and potential energy is zero as the assembly is released from rest in the horizontal position. So we have to find the final kinetic energy and final potential energy. And the change in potential energy is due to the potential energy of wheel and the potential energy of yoke. So we have the potential energy of wheel, that is equal to mw multiplied g multiplied delta hw, and for yoke it is myg multiplied delta hy. And for wheel, its distance from the point O is OA, and while for yoke, this distance is OG. And here you see the term minus sign represents the vertical displacement of the center of mass of the yoke in relation to a reference point. And you see the negative sign is convention indicating that the displacement is downward, because you see if we move from point A to point A dash, the height is decreasing. And for kinetic energy, it is due to the kinetic energy of wheel and yoke. And as you see, both yoke and wheel is performing a rotatory motion. So the kinetic energy for both wheel and yoke is 1 divided by 2 IW square. And for wheel, the moment of inertia is mr square, while for yoke it is mk square. And you see we have this W, that is the rotational velocity. So we can write this as translational velocity divided by R, because we have already discussed this in the previous lecture when we solved problem 1. And to calculate the change in gravitational potential energy of system, we have this formula. So we have to substitute the value. So we have 4 kg for the mass of wheel, 3 kg for mass of yoke, 9.81 meter per second square for the force of gravity, 0.5 meter for distance OA dash, and 0.3 meter distance for point OG. So we get the final potential energy, that is equal to minus 28.45 joules. And to calculate the change in kinetic energy of system, we have this formula. So we have to substitute again the mass of the wheel, that is 4 kg, mass of yoke, that is 3 kg, the radius of wheel, that is 0.25 meters, and the radius of gyration k, that is equal to 0.35 meters, and again the distance between points OA dash, that is 0.5 meters. So we get the final kinetic energy, that is equal to 4.735 multiply the square of velocity. And you see here the work done on the system by all the external forces is that the gravitational force is zero. So it means that the work done from initial to final position is zero. And we have a work energy equation. But you see here the initial and initial kinetic and potential energies are zero, so it becomes like this, and also the work done is zero, so we get the final equation, that is the change in kinetic energy plus the change in potential energy at the final position is equal to zero. So you see we have to substitute work done values and a change in kinetic energy values and a change in potential energy values. So we can find a value of velocity that is equal to 2.45 meter per second.